in an account for 10 years and is gaining 20% interest, how much will you have? So on part A, guys, we're just getting interest one time a year. So this is when we just use simple exponential growth and decay, which is y is equal to a times b raised to the x. So a is our initial value, right? Our initial value, and b is our growth or decay factor. In this case, growth. So we're gonna have y is equal to, we started out with $500, and then our b is our growth factor. 100% growth plus 20 additional percent is 120%. How do you rewrite that as a decimal? 1.20 or 1.2, and then raised to the 10 years. Type it in. Go.
3095.
Okay, so we have $3,095.87, right? Okay, now pay attention because now it's changing. The interest is now just not happening once a year. It's now compounding continuously. So remember, that means you're always getting interest at any given time of the day, at any given second. This is when we use the formula P times E raised to the RT, PERT. So y is equal to, our put down amount is 500. E is just a number raised to the RT. Now here's the thing. PERT is the special formula where R does not change. So we're just going to use 0.20. That's 20%. You do not add a 1 to that one. And then the time in is 10. So times 10. Go, type it in. Make sure you can type it in. 3694.53. Did everybody else get that? Okay, then I can trust it. Okay, awesome. Questions? Okay, we good with those? That was essentially what we learned in lesson 1 and 2. Okay, awesome. Okay, now we're getting to 8-3. Today we're going to be starting with our logarithms. So this is our exponentials and logarithms unit. So today we're going to get into all the basics of logarithms. So we're going to be learning a ton. So make sure you're paying attention. Okay, so first of all, we've been dealing with exponentials. Exponentials have the form y is equal to a times b to the x right here. If we look at this, do you see how this is an exponential? Y is equal to b to the x. Everybody? That's an exponential function. B is my base, right? Okay, so one thing to note is exponentials are the inverse of logarithms, and logarithms are the inverse of exponentials. I'll say that again. Logarithms are the inverse of exponentials, and exponentials are the inverse of logs. So what an inverse does, guys, is we know that an inverse undoes something. So for example, 2 times x is multiplication. What undoes multiplication? Division. Do you see how it undoes it? So multiplication and division are inverses of each other. That's exactly what logs and exponentials do to each other. They undo each other. So y is equal to b raised to the x is the inverse of y is equal to log to the base b of x. And y is equal to log to the base b of x has an inverse, y is equal to b to the x. So we can literally, guys, we can take an exponential and we can change it to a logarithm. We can take a logarithm and rewrite it as an exponential. So here's a couple of things we need to understand is how to say this correctly and understand where these things come from. So this is y is equal to log to the base b. So it's read log to the base b. You see how this is base b? This is base b to the x power. This is log to the base b of x. So this x is trapped inside the logarithm. Does everybody kind of understand not what this is, but how it is? Okay, awesome. Okay. So one thing to note is this base b is always written really small. It's kind of like a subscript down here, and then of x. Okay. So I'm going to show you algebraically how to get from here to here and how to get from here to here. Because we're going to be switching back and forth. Okay, here's the algebra behind y. So if you want to take some notes, you can. So if I said to you, take the exponential, y is equal to b raised to the x, and let's put it as a logarithm. So we're starting out with an exponential. We want to make it a logarithm. So to find the inverse of all functions, don't we switch x and y? Remember we found inverses on the last test? Yeah. If I said you find the inverse, don't we switch x and y? Let's do that. So we have x is equal to b to the y power. Now notice, from here we're trying to solve for y, but it is stuck in the exponent of base b. Now you cannot divide by base b. That is not a way to get y down out of the exponent. So if you're solving for something and you're solving for it and it's up in an exponent, the only way to get base b to go away is to do the inverse, which is log to the base b. So we're going to take log to the base b, and we've got to do that to both sides of the equation. So I did it to both sides. So now over here, we have log to the base b of x, log to the base b of x, equals, now look, log to the base b and base b cancel out, that's what inverses do, equals y. And now we have written it in y equals log to the base b of x. So we just rewritten that as a logarithm. Just using algebra, right? So you see how it's just algebra. Okay? Okay, let's go the other way. We're going to practice more. If I said to you, rewrite this logarithm as an exponential or find the inverse, what we would do is we would switch x and y, just like we've done with all of our other finding inverses. So we have x is equal to log to the base b of y. Now, isn't y trapped inside log to the base b? The only way to undo log to the base b is to apply the inverse, which is base b. Very good. So we're going to base b, both sides of the equation. So now on this side, we have base b raised to the x equals base b and log to the base b cancel out y. And we're done. Isn't solving getting at y equals the function when we're done? Okay, so that's how we switch back and forth. So we can write an exponential as log and log as an exponential. Okay, here we go. Number 1 on the worksheet. It says, read the instructions. It says, rewrite each equation in logarithmic form. So I want you to notice something. We're not solving for anything. Isn't this a true statement? 4 to the first power equals 4. Yep. So right now, all we're doing is we're just rewriting it in the correct logarithmic equal form. So this is base 4 to the first power. So how do we undo base 4? Log to the base 4. So we're going to log base 4 both sides of the equation. Okay, everybody write that down. So now look. Log to the base 4 and base 4 cancel out. So we have 1, you see the 1? Drops down. Equals log to the base 4 of 4. So we just took and put it from an exponential to a logarithm. Right now you're not seeing a point to this, and I get that. Later there's a point to it, okay? Okay. I know. Right now it's kind of like, well, why did we do that? You're right. I'll explain why later, okay? Next one, if I said to you, rewrite this as a logarithm, notice it's base 20 to the second power equals 400, which is a true statement. So we're going to take log to the base 20 of both sides, right? Okay, so let's write this correctly. I want to see everything written out all pretty. Log to the base 20 and base 20 cancel out, so 2 drops down. So we have 2 is equal to log to the base 20, you got to write it down small, of 400. This is just rewriting it in logarithmic form. Yep, those are the answers. Okay, number 3. Base 11 to the 0 power equals 1. If I said rewrite it as a logarithm, we need to undo base 11. So we would take log to the base 11 of both sides of the equation. Log to the base 11 and base 11 cancel out. So 0 is equal to log to the base 11 of 1. Just rewriting it as a log. We almost good? Are you guys good? You ready to go? One more, are you good? You're good? Okay. What I'm going to have you do then is go to 19 and do those. So you're taking the exponential and rewriting it as a logarithm. So we're going to 19. So I just want to make sure you understand. Let's just do 1 out of 19 section. So go to 19, find this one. Let's at least do this one. What people want to do is they'll see, because it's not in the correct order, in their minds, they'll try to do log to the base of 1 over 64. But do you see how this is our base, even though it's on this side of the equation? Because it's 1/4 raised to the 3rd power. So we need to do log to the base 1/4 of both sides of the equation. So now over here, that's log to the base 1/4 of 1 over 64 equals log to the base of 4th, and a 4th cancel out equals 3. So just make sure you're doing the correct log to the base, whatever is raised to the exponent. That's your base. Yep, okay, 19 finished. Go for it. Everybody locate problem number 23. Okay, my examples are 2 out of that section. So they're all on that left-hand column, so look down with your eyes. We're going to do this one first. Log to the base 12 of 1 over 144 equals -2. Now let's read the instructions. It says take the logarithm and rewrite it as an exponential. So instead of having it as a logarithm, we're going to rewrite it as an exponential. So what we're going to do is say, I need to undo log to the base 12. What undoes log to the base 12? Base 12. So we're going to base 12 both sides of the equation. Now base 12 and log to the base 12 cancel out. That's what inverses do. So we have 1 over 144 equals 12 to the negative 2 power. So we've just rewritten it as an exponential instead. Now look, you should be able to check to make sure you did it right because it should be a true statement. Is 12 to the negative 2 1 over 144? Yes, think about it, guys. If we take 12 to the negative 2, we've got to take and flip it over a fraction, so that's 12 squared, leaving me with a 1 on top, so that's 1 over 144. So our statement is true. Okay, let's do number 23. Now, what I want you to notice that's very interesting on this one, sorry, number 23, this one. Log of 10 equals 1. There's no base. Do you see how we're missing the base? Nothing there. So what it really is just like if we have a square root, what's really secretly there? 2. Very good. Just like a square root really has a 2 there, if there's nothing there, there's secretly a 10 there. I know. So if you have nothing there, just write in your own 10 because it's really there. Now let's rewrite it as an exponential. So we need to undo log the base 10. So we'll base 10 both sides of the equation. So base 10 and log the base 10 cancel out. So we have 10 on this side of the equation equals 10 to the first, which is a true statement, so we know we've done it right. So do you see how we can take a logarithm and rewrite it as an exponential? Awesome. Let's do that one. So what I want you to do is problem, which one is doing that? 23. Go to 23 and finish that bad boy up. Okay, what the heck? Where's my, finish 23 up. That's what I had down here and I erased it. Finish 23. Go, ready, go. Everybody look right here. If I said to you, simplify this, notice there's no equal sign. Like all the other ones were just true statements we were rewriting. This one wants you to figure out what it's equal to. So we don't know what it's equal to. It says evaluate it. So let's set it equal to x, because we have no idea what it is equal to. Yeah, this is number 5. So it says evaluate. Now notice, once again, there's no equal sign. It means what is log to the base 5 of 1 over 125 equal to? So we're going to set it equal to x, and we're going to rewrite it as an exponential and see if we can evaluate it as an exponential, because that's usually easier. So how do we undo log to the base 5? Base 5, right? So we'll base 5 both sides of the equation. So look what happens. Base 5 and log to the base 5 cancel out. So we have 1 over 125 equals 5 to the what power? So now think about it, guys. If we don't know, now we're going to solve. Do you see how we're going to just solve it? So let's figure out what power of x will give us this answer. So let's see if we don't know, let's test it out. 5 to the first power is 5. 5 to the second power is 25. 5 to the third power is 125. Wait a minute, but they flipped it over a fraction. So what does that mean? It's negative. Way to go. So our answer is not x. We're going to go back up and say our answer was negative 3. Not 5, sorry, not 5 to the negative, it is 5 to the negative 3 right here, right? No, we won't write the 5 in. So what I'm saying is 5 to the negative 3 is this, correct? So wasn't our answer negative 3? X equals negative 3, guys. Okay, x equals negative 3. But here's why I don't want you to write x equals negative 3. That's not wrong. That is our answer. Our answer is negative 3. But they said, what's log to the base 5 of 1 over 125? We said it was negative 3. Do you get what I'm saying? Yeah. Yep. Because we got x equals negative 3. So it's just negative 3. So do you see how taking a log and writing it as an exponential can help us simplify it? Okay, let's do another one. Number 6. So log the base 3, we don't need to write x equals negative 3. I won't mark it wrong, but this simplified to be negative 3. Okay, so right here we don't know what it's equal to, so let's say it's equal to x. Now let's undo log to the base 3. So we base 3 both sides of the equation. Base 3 and log to the base 3 cancel out. So 27 equals 3 to the what power? Yeah, so answer what it is now. If you don't know, test it out. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. So our answer is x equals 3. So log to the base 3 of 27 equals 3. Our final answer was log to the base 3 of 27 equals 3. Okay, do 7 and 8. Do 7 and 8. Yes, good. 7 is 1. Very good. Good and good. Just push pause on this video. Okay, so now I already talked about this briefly, but just a reminder, log to the base 10 will look like this. Y is equal to log to the base nothing means really is secretly a 10. So we can just write in our 10s. So everybody, if I said 2, go to number 20 and locate this problem. So it says, what is log of 100,000? So isn't this the same thing what we just did? We don't know what it's equal to, so we can set it equal to x, right? And now we need to undo. There's a secret 10 in there. So I'm going to write that in. We need to undo log to the base 10. So we base 10 both sides. Base 10 and log to the base 10 cancel out. So 100,000 equals 10 to what power? Yeah, 10 to x power. So what power? What's my answer going to be? Try it. If you don't know, go into your calculator. Do 1, 2, 3, 4, 5. Nope, it's not 10, but good try. No, guys. OMG. Okay, everybody listen up. 10 to the first power is 10. 10 to the second power is 100. Right? It's 10 to the fifth. So look, 10 to the fifth. So x equals 5. So our answer was log to the base, log of 100,000 equals 5. Not 10 to the 5, just equals 5. That's our answer is 5. I'm going to explain in just a second. Now notice, this is log to the base 10. I want you to look at your calculator. Now, if your calculator is more advanced, you still need to learn it this way. I will expect you to do it this way, and I'll explain why in a second. So everybody, look at your calculator. Do you see how if I wanted to calculate log of the 100,000, I could just use my calculator? Now look, it came out. But what happens, notice it was log and it's always base 10, isn't it? So the only time we can use our calculator is if we have base 10. So did you see how we had to rewrite them as exponentials otherwise? Okay, awesome. Now one more thing. There's going to be times when you have to use your calculator and be able to type it in base 10. And that's what brings me to the next thing. Okay, so when you can't evaluate it by rewriting it as an exponential, like meaning, for example, look at number 20. I'm going to show you number 20. Let's start out this one how we've just been doing all of our others. So go to 20 and we're going to look at this one. Log to the base 4 of 32. Let's try to evaluate that the same way we just were doing it. So didn't we set it equal to x? Base 4 both sides, everybody. So we have 32 equals 4 raised to what power? So let's test it out. 4 to the first power is 4. 4 to the second power is 16. What's 4 to the third power? 64. Yikes. Do you see how none of our powers are ever going to be, it's never going to put us there. So this means that for x, it's not a pretty answer. It's not a straightforward answer. So we would want to be able to use our calculator to solve this for us. So I'm going to erase. We would not solve this one this way. We tried, which was a good try, but it didn't work. So that's when we would use the change of base formula, which is this. So the change of base formula is a way to rewrite log to any base of x as base 10. So we can take this log to the base b of x and we can rewrite it as the same base, base 10. Notice base 10, base 10. So you can take and rewrite it in its equivalent form. So this is the same thing as this. We can put it as this. So if we have log to the base b of x, you can rewrite it as log of x divided by log of b. So here's a little trick for you to help you remember. So this is a mini little subscript, right? So it's always log of the big thing divided by log of the mini thing. Not big in number, but big in size. Do you get what I'm saying? That's a stupid little trick. Do you get what I'm saying? Log of the bigger thing divided by log of the mini thing. So that's just a way of now you can use your calculator. So look, log the base 4 of 32. We tried to evaluate it the way we've learned before, but now we can't because it didn't work. So instead, we're just going to use the change of base formula. So we can literally rewrite this. This is equivalent to, using the change of base formula, log of 32 divided by log of 4. And now we can literally just type it into our calculator. Because it's base 10. So watch. Log of 32, close your parentheses. Log of 32, close your parentheses, divided by log of 4. Hit enter and it evaluates it for us. 2.5. Good job. You would guess that. Oh, you just thought about it. Okay. Oh, gotcha. Got it. Okay, cool. So we get 2.5, which let's write it as a fraction maybe. So math enter, right? Yep. Which is 5/2. So our answer is 5/2 or 2.5. I haven't decided yet. Yes. Okay, so let's do this one using the change of base formula. How would I rewrite it? Log of 128 divided by log of the mini thing, the subscript, divided by log of the subscript. Log of the big divided by log of the small. 7. Was that pretty easy? That one's on there somewhere.
I did that one. How do we do the other one?
And you, what? What? You don't get it? Oh. Yeah. What do you mean? Okay, I want you to look up here and then we'll talk. Okay, so everybody look at this last example. It's not on your worksheet, but please look, because I'm going to ask this specifically on the test. I'm going to say, simplify by change of base formula and also rewriting it as an exponential. So we're going to solve both ways here. So let's first rewrite it as an exponential. So wouldn't we do this one by setting it equal to x? Everybody watching, because this is what's going to be expected. Base 3 log of base 3 cancel out. So we have 1/9 equals 3 to the x power. 3 to what power? -2, right? Flip it. So then you would do it using the change of base formula. You would rewrite it as log of what? 1/9, right? Divided by log of 3. Now remember, we always put the mini subscript above. So we just type that into our calculator and you do, and you get -2. So it's just getting it 2 different ways. You can do either or. Okay, 220, ready to go. We're running into this problem at this point. When you have log of -32 divided by log of 2 and you try to type it into your calculator is going to say error. Here's why. We can never have a negative inside of a logarithm. It's just not possible. So this would be no solution or no simplification. Or just can't is easier to write. You can't do it. This is where this is involved because they're easy points. If I say you simplify this, simplify. Log of base 3 and base 3. Do we need to do all this hard work? No. What happens automatically? Log of the base 3 and base 3 cancel out. What would my simplification be? -2. Does everybody see? Okay?
Oh.
Right? Because they're inverses of each other. Log of the base 3 and base 3 are inverses of each other. Isn't that what do each other? Okay, let's look here. Log of the base 4 of base 4 to the 16. What would my answer be? Guys, right? Log of the base 4 and base 4 cancel out. You see how it's just 16 very quickly. You need to be able to see them that quickly. This isn't on anything. You're just looking up here. So now that we're all on the same page, do we need to re-go over this? Instead of be looking for what I look for. No. Look, log of the base 3 and base 3 cancel out. So we get -2. So it's just simplifying. Does that make sense? Right here, log of the base 4 and base 4 cancel out. So 16 is just my answer. Oh yeah, right here. Okay, well base 3 and log of the base 3, aren't these inverses of each other? So don't they undo each other? So my answer would be 10. Everybody seeing how quick this is? 7 log of the base 7 is 20. Good. Okay, here we go. So it says find the inverse of the function. So just watch. Watch how quick I'm going to go through this. And then I'm going to let you practice. So to find the inverse of a function, given an equation, don't we always switch x and y? So x is equal to log of the base 3 of y. Now you have to solve for y using algebra. So don't we need to undo log of the base 3? Base 3 both sides? So we have 3 raised to the x equals base 3 and log to the base 3 cancel out equals y. So isn't my answer y inverse equals 3 raised to the x? Okay, let's do another one where a little bit more algebra is involved. Everybody watching so that you know what would be expected. So we would switch x and y. X is equal to log to the base 5 of 2y. Now would I divide by 2 right here? No, it's trapped inside the log. So don't we need to first undo the log? Base 5 both sides. 5 to the x power equals 2y. Next step, divide by 2. Now let me show you what would be expected. So we have y is equal to that 5x divided by 2. The correct way of writing it would be to write it like this. So y inverse isn't that, can't we pull out a 1/2? Isn't 5 times a half the same thing as 5 divided by 2? So we have 1/2 times 5 raised to the x power. And now I've written it as an exponential in the proper form. 5 divided by 2 is the same thing as 1/2 times 5. I feel like some people are confused. Guys, 3 divided by 2 is the same thing as 3 times a half. So does everybody see how I just rewrote it like this? If you don't rewrite it like that, I'm going to say rewrite it like that. Okay, so now look, it's in exponential form. Initial value factor. That's why I push you to do that. Okay, switch x and y. X is equal to log to the base 2 of y plus 1. Can we subtract 1 right now? No, it's trapped inside the log, so base 2 both sides. 2 raised to the x power equals y plus 1. Next step, subtract 1, right? So y inverse is going to be 2 raised to the x minus 1. So now isn't this a shifted exponential? Down 1, just saying? Okay, that would be my final answer. So last one, most advanced one of all. Switch x and y. So we have log to the base, what? Log to the base what? 10. Okay, good. What would be my first step? Any ideas? Good. That is exactly what we have to do first. We can't undo the log without getting rid of this 1. So we have x minus 1 equals log of 2x minus 3. Now, how do we undo log? 10. Isn't there a secret base 10 in there? So we base 10 both sides of the equation. So we have 10 raised to the x minus 1 equals 2x minus 3. Next step. Good. Add 3 over. Oops. Add 3 over. So we have 10 raised to the x minus 1 plus 3 equals 2x. And then we would. That's a y, isn't it? Same thing though. Divide by 2. And then let's go the appropriate answer. So y is equal to, isn't this 1/2? Oh yeah, let me make sure you understand something. You can never take a base and divide it with this. Like 10 raised to the x minus 1, you can't divide it with 2. Everybody good with that? Because that's not just 10 divided by 2. It's 10 raised to the x minus 1. So you cannot divide by 2. Okay, so we would have 1/2 times 10 raised to the x minus 1 plus what? Nope. Plus 3/2. Wasn't 3 also divided by 2? Oh. So this would be my answer. So wouldn't this be a shift of right 1 up 3/2? Compression of 1/2. Just if we were going to go that far. You could in x plus 1. What do you mean, Prim? Oh, I see what you're saying. Having it out here. Yeah, that would work. Okay, do 26 go. Do 26 go. All the time line. Yes. Okay, so what we're going to do is flip to problem number 10. And I need you to cross out B because they wrote down the wrong thing. B should be not 1/2 raised to the x, but 2 raised to the x. So we're going to graph log to the base 2 of x, and we're going to graph its inverse, y is equal to 2 raised to the x. We just figured out how these are inverses of each other. You take one and switch x and y and then solve, you'll get the inverse. So what I want us to do is focus in first on graphing y is equal to 2 raised to the x power. That's what we learned on day 1 of this class. So remember we do this by plotting points. So let's plug in -2, -1, 0, 1, 2. I'm going to plot points. And remember, I let you use your calculator. So pull it up. Everybody should be doing it. So you type in 2 raised to the x power and hit graph. There's my exponential growth equation. Now look at my table of values, second table. Once again, so we're looking at this. We're looking at these points. Now, as x, so everybody look at my picture here. As x is getting smaller and smaller, isn't our function getting, as our function's growing, as x is getting smaller and smaller, isn't our function growing to 0? Look, as we go smaller and smaller, do you see how it's just getting smaller and smaller, closer and closer to 0? Okay, so that's what our asymptote is. That's where our asymptote comes from. So remember, with our exponential, we have an asymptote, a horizontal asymptote at y equals 0. And now let's plot some points. So tell me what the point was. Negative 2.25, right? Negative 1.5. Guys, are you looking at your table of values? Over 1, 2, over 2, 4. So let's plot those points. So negative 2, I'm going to go a different color here, maybe like that bright green. So negative 2 up barely any. Over negative 1 up halfway. Over 0 up 1. Over 1 up 2. Over 2 up 4. So now I can see my exponential growth equation here. Yep, at y equals 0. Yes. Okay, let's plot 3, 8. Perfect. Let's plot that one too. 3, 8. Good idea. Let's plot everything we can. So now, how do we find the inverse of a bunch of xy points? Can anyone remember?
Yeah.
Good. Way to remember, Luis. Can't we just switch x and y?
Yeah.
So the inverse of y is equal to 2 to the x would be log the base 2 of both sides. So our inverse is y is equal to log the base 2 of x. So let's switch those xy points and then we'll have our graph. So we'd switch x and y. So 0.25, negative 2. 0.5, negative 1. We're switching x and y because that's the inverse. And then 0, 1. Other way around. 1, 0. And then over 2 up 1. Over 4 up 2. Let's plot those. And then over 8 up 3. Okay. So let's plot those points. I'm going to plot it in blue. So you're going over barely any and then down 2 units. We're going over halfway and down 1 unit. Over 1 up 0. You're graphing this on your paper too. Over 2 up 1. Over 4 up 2. So now, isn't this just getting smaller and smaller here? If this is getting smaller and smaller, isn't this getting smaller and smaller? So it's just approaching 0 there again. So now that asymptote is no longer horizontal. It's now a vertical asymptote at x equals 0. So do you see how now, for a logarithm, we have this asymptote? We have a vertical asymptote at x equals 0. That's the important thing to get from this. So the logarithm has a horizontal asymptote at x equals 0. Sorry, a vertical asymptote. I said horizontal. I meant vertical. Vertical is up and down. Okay, let's talk domain and range on both of these. So let's look at our green function, our exponential. What's the domain from left to right? Yeah, we're going to talk the green exponential from left to right. Negative infinity to positive infinity. Our domain is all real numbers. What's our range for this? 0 to infinity. There's a point to all of this, so please stay with me. So let's look over here. Our domain and range. Let's look at our logarithm. What's our domain? 0 to infinity. And what's our range? Negative infinity to positive infinity. Now remember, don't we know that this domain will be this is range? And this one's domain will be this one's range, which makes sense. It all makes sense. So a couple of things I want you to notice about a logarithmic equation, okay? So we have log the base 2 of x. This had no shift left and right, no shift up and down, correct? And we had a vertical asymptote at x equals 0. So now let's change this and move this a couple units to the right. So let's say we shifted it right too. Wouldn't that take my asymptote and move it like this? Yeah. So now my new domain would be 2 to infinity instead, right? So if there was a shift left or right, you see how that just quickly, I could just think about it and say that changes my domain. Does that change the range if I shift it up or down? Let's picture ourselves taking the blue thing and moving it up. Won't it still grow down and this way forever? Okay, so that won't change our range. Our range for all logarithms is always all real numbers. The domain is either going to be 0 to infinity, or if there's a shift left or right, it'll be that. So let's say I took and shifted it back 5 units. Then we would have a vertical asymptote at -5, and it would look something like this. The domain would be -5 to infinity, and so on. Okay, let's answer these questions here. Okay, so now we're going to be shifting log equations. So basically, just ignore this. We're going to get right into the logs. Shifting for all functions works the same. Grouped in with x as your shift left and right, you go opposite. Out on the outside is your shift up and down, our sign stays the same. So just look at this example with me. If I said to you, describing words the shift from the parent function, you would say, what? Right? 1, up, 4, stretch of 3. Now the stretch of 3 just means it gets larger quicker and larger, smaller quicker. So we're going right 1. Now didn't we originally have an asymptote at 0 for a logarithm? This is the part, okay guys, do we need to take a break? Here's the thing, I don't want to make you graph these. But you have to give me the domain and range. So that's why I'm having you think about the graph, because it helps with domain and range. So if I need to, I can make you graph them, but I'm not going to make you graph them if you can figure out how to do domain and range. So everybody, they shifted right 1, up 4, stretch of 3, correct? Okay, originally our asymptote was here. Didn't it go right 1 now? So this is right 1, and now we're shifting up 4, okay, so it's just up here, correct? Now looking at this, that doesn't change our range. Wouldn't our domain now be 1 to infinity? Because it shifted right 1, didn't it? So wasn't that my new asymptote? Yeah. But my range was still all real numbers. Isn't it still going down and up forever even though it shifted up or down? That's all I'm getting at. The 3 doesn't affect anything besides the acceleration was quicker, like faster. Is that what you were going to ask? About the 3. Yep, right 1, up 4. Because we always go opposite, right? It shifts left and right. Yep, because it used to be at 0, so now if you take that function and move it, it won't let change the asymptote. Yep, for logarithms. Okay, so let's look at 11. Here we go. 11 on the worksheet. It says, describe how the graph of each function compares to the parent function. So looking at number 11, everybody get there. So you're not doing extra work because we're doing it together. What I want you to do is write down the parent function. A parent function means the same function but not shifted. So our parent function for this would be log to the base 3 of x, because that would be non-shifted. Our shift is right 5, shifts left and right are grouped in with x, and then we're going up 3. So now if you need to think about a rough sketch, right 1, 2, 3, 4, 5, we would have a new asymptote at right 5, correct? And then shifted up 3 would just be somewhere up there like that. So our domain is what? 5 to infinity. Very good. And our range is all real numbers. The shift up 3 didn't affect my range. Okay, number 12. Here we go. Describe the shift from the parent function and all this. So our parent function would be log to the base 4 of x. Y is equal to log to the base 4 of x. It shifted left 2, down 1. So our domain would be -2 to infinity, and our range would be all real numbers, correct? Okay. Do 22 and 27. So this is a formula for intensity levels and magnitudes on the Richter scale of earthquakes. And it's base 10, so base 10 on the Richter scale. So the Richter scale is just a way of counting. So notice this is log to the blank base. So we know there's secretly a base 10 in there, but we don't need to write it. So this is the formula used to compare intensity levels and magnitudes of earthquakes. And you're going to see how crazy, just even like 0.2 difference of magnitude is going to change how intense it is significantly because it's base 10. So this stands for if you have an earthquake 1 and earthquake 2, if you're comparing earthquake 1 to earthquake 2, you'll do log of intensity 1 divided by intensity 2 equals magnitude 1 minus magnitude 2. So here's my first example, number 9. It says, and these are true statistics, you guys, these are true earthquakes. So let's compare them. And it's kind of interesting because some of these cities are utterly destroyed, where others are like, it's like nothing even happened. And you'll see what I mean in just a second. So in 1812, an earthquake of magnitude 7.9 shook Madrid, or Madrid, how do you say it? Somebody will know. Madrid. How come you guys know how to say that? Okay, that's why. Okay, well, I'm definitely not. So, okay. All right. So, because of class. Okay. So, anyways, in 1812, an earthquake of magnitude 7.9 shook New Madrid, Missouri. Compare the intensity levels of that earthquake to the intensity of each earthquake below. So, everybody, we're going to compare this true earthquake of magnitude 7.9 to 7.7. Now, you would think they'd be pretty close in how did they destroy the cities versus one versus the other. Because isn't 7.9 not that much larger than 7.7? But you're going to be surprised. So let's plug it into our formula. So here we go. We have log of I1. We don't know the intensity one. That's what we're comparing. Divided by I2 equals magnitude 1 minus magnitude 2. This is our first earthquake, 7.9. Minus, we're comparing it to 7.7. So using algebra, we have log of I1 divided by I2 equals 0.2. Now solve for intensity. We're trying to compare the intensities. They're trapped inside the log, so we're trying to solve for intensity 1. So let me move this down, because it is really annoying that it's in the way. Okay, down here. There we go. So, what do we base 10 both sides? We're trying to get I wrote I2, but I meant I1. So we'll base 10 both sides. Log of base 10 and base 10 cancel out because we know there's a secret base 10 in there. So then we have intensity 1 divided by intensity 2 equals 10 to the point 2. Give me that. 10 raised to the point 2 is 2? Oh, sorry. I was like, really? Okay, 10 raised to the point 2 power. What is that? 1.5. 1.5. Okay. So now, if I want to take this literally, couldn't I solve for I1, intensity 1? Wouldn't we multiply both sides by intensity 2 to get I1 alone? Okay, let's multiply both sides by I2. Now let's see what this reads, because look, those divide out. So we have intensity 1 equals 1.5 times that of intensity 2. So how much more intense was the first earthquake than the second? 1.5 times. So that city was way more destroyed because 1.5 times. Does that make sense? A lot more than what you'd think. And that's because of the base 10 on the roof. Yeah, so because look, it asked, our answer is this. So it said, how many more times intense was the first earthquake? We literally look at our equation, it literally says it was 1.5 times that intensity level of the second. So 1.5 times. As strong. As intense. Yep. Let's do this one. So we're comparing it to magnitude 3.2. We're comparing the original 1812 or whatever, and it was 7.9, wasn't it? So we would say log of intensity 1 divided by intensity 2 equals 7.9 minus 3.2. You're going to see how crazy of a difference this one is. So we would undo the intensities to get the intensities alone by taking base 10. So log of the base 10 and base 10 cancel out. So intensity 1 divided by intensity 2 equals, I should have calculated that, it's 4.7. So we have 10. Yep. So 10 raised to the 4.7. So we know that intensity 1 divided by intensity 2 equals 50118.7. Is that what you get? Type it in. Now multiply and solve for intensity 1 because it said compare intensity 1 to intensity 2. So we'll multiply both sides by intensity 2 and we get the intensity of the first earthquake was 50,118.7 times the intensity of the second. So this was extremely, extremely more intense. 50,118 times as strong. Wow, it's crazy. So this was utter devastation, where the other one was just some destruction. Okay? All right. Which I'm not a meteorologist, so I don't know exactly how much destruction, but kind of interesting. Okay, do 21. Same exact thing. I wasn't recording during any of that, dang it. Oh. Okay, this is times 10. Thanks for catching that to the negative. Negative.
1.2. Oh, wait.
Okay, so this would be my final answer. And we would leave it like this because we could move the decimal back. Ding, 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 ding. But I don't need you to. Just leave it like that. Well, I'm not going to make you. Like, leave it like that. Because that's a scientific number. The reason we like scientific numbers is because we don't have to write out all the decimals. But do make sure you're writing times 10 to the negative 8, because 6.3 is very different than 6.3 times 10 to the negative 8. Was it negative, by the way? Please. You guys got to correct me. Oh, okay, never mind. Oh, sorry, my fault. Hey, do a couple on. No, everybody watching or you're going to get it wrong. You don't even need to do more of those. If you've done 2, that's enough. Like, I'm not going to require you to go home and do more. Okay, we know. Focusing, refocusing. Y is equal to base 3. Oh my gosh. So we have y is equal to base 3 raised to the x. What's the inverse? What do we do? Log the base 3 of both sides. So base 3 undoes log the base 3, and log the base 3 undoes 3. So here is an exponential function. Y is equal to e raised to the x, right? We've already talked about how that's just a special exponential. So to undo e, it has a special logarithm. ln. So what undoes e? ln. What undoes ln? E. Does everybody understand? So let's solve this equation. Actually, go to 13 and 14. It says use a calculator to approximate. Type in ln of 64. There's an ln button on your calculator. 4.159. Go. Write it down. The ln of 5.1 is 1.629. Okay, awesome. That's it. Now let's solve an exponential equation here. I have a random spot to put this, so let's just go for it. Finish up. So it says solve. So notice we're doing this one. Number 15, everybody. Now pay attention because this is important. It says solve. Now notice, isn't our variable up here in the exponent? Okay, we're going to get that along piece by piece. So our first step is to get the exponential all by itself. Base e has to be all by itself. So we divide by negative 8. So then over here, we would have base e raised to the b minus 1 equals negative 20 divided by negative 8. Let's do the fraction. So wouldn't that be, they both divide by 4, don't they? 5 halves. Now from there, you'd say, I need to get b down from the exponent, but I can't divide by a base. That's unallowed. How do you undo base e? ln. E has the special one. Does that make sense? Log of the base e is the same thing as ln. So we would ln both sides of the equation. ln and e undo each other. So that drops down b minus 1, which equals ln of 5 halves. Next step to get b alone. Add 1. So b is equal to ln of 5 halves plus 1. I would like to see that answer. And then also, you can type that into your calculator. Let's do that too. I want to see both. So you have ln of 5 halves plus 1. So b is equal to, type it in, and you should get 1.9. I want both answers. Let's do, actually, I think you guys are good. Don't you think?
Yeah.
Okay, so the last few minutes, what I want you to do is work on problems 15 through 17 and check those off with me. Well, I would have just marked you all off on homework because I would have said, well, duh. So it's a very smart question to ask.